Morning, everybody, or whatever time you're watching this. We are talking about ionic bonding. We're moving into a new chapter, and this is chapter 7. So we are moving right along. We are starting to get into actual chemical reactions here. So ionic bonding, that is your strongest bonding. You're going to notice that that's where all your solids, how they bond. NaCl is ionically bonded. Sodium bicarbonate, which is baking soda or baking powder, is ionically bonded. Okay, all your solids are pretty much ionically bonded. What is ionic bonding? Ionic bonding just involves a transfer of electrons. Okay, we'll talk about two types. There's ionic and there's covalent. Covalent, they share electrons. Ionic bonding involves a transfer of electrons. So atoms are actually giving up an electron or taking electrons. And there's a way we can tell if a reaction is ionically bonded, and that's by using our periodic table. So this is something I want you to do with your periodic table that you have. It doesn't matter which one, just as long as you do it so you kind of know what I'm talking about here. So have your periodic table out. Okay, so the periodic table, this is my rough outline of it, is split up into two sections, metals and nonmetals. Metals are mostly on the left side of the periodic table, nonmetals are mostly on the right. But there's this nice dividing line, and it's called the stair step. You could probably look at a periodic table online and find one that has this, but if you don't, okay, it occurs right around here, and I will label some elements for you so you know where this stair step actually resides, okay? Sometimes I forget where it resides, so it's always good just to refresh on this. Okay, so the stair step, you have boron on the right side of the stair step, silicon, you have arsenic, you have tellurium, and then you have astatine, and it falls all the way down. Okay, so draw that little bold stair step right here on your periodic table when you get a chance, okay? And all you need to know is that everything on the left side of this stair step is a broad definition of metals, right? We could get more specific and say alkali metals, alkaline earth metals, transition metals, metals, but pretty much for the most part we're saying that everything on the left side is metals. Everything on the right side of this stair step is a non-metal, okay? One exception over here is hydrogen. We treat it as a nonmetal as well. Okay, so ionic bonding is going to involve a metal and a nonmetal. So I'm going to put in parentheses metal to nonmetal bond. So if I ask you what is ionic bonding, you'll say either it involves a transfer of electrons, or you'll say it's a bond between a metal and a nonmetal. Either one of those is fine with me. The more accurate definition is that it involves a transfer of electrons, but for our sake, I'm cool with that, or metal or nonmetal. All right, so let's talk about something else real quick. Let's talk about the Octet Rule, which we talked about a little bit when we were dealing with our trends. So we will talk about the Octet Rule a lot, but pretty much it is elements like to have 8 electrons in their outer shell. Okay, in their outer shell they like to have 8 electrons, Or a more accurate, broad statement is that filled outer shell. Okay. As we get down lower, they don't have 8 in their outer shell. They have terms of, they could probably have 18 in their outer shell. Okay, and then as you get down those lanthanides and actinides, it ends up being 24, 26, 32 in their outer shell. Okay, but for the most part, we'll just say that they like to have 8 in their outer shell. So why does this matter with ionic bonding? Okay, let's have an example with our most basic ionic bond, which is sodium and chlorine. So sodium has an inner level of 8 electrons and an outer level of 1 electron. So what sodium is going to do, let me make this more clear. So what sodium really wants to do is it wants to give up an electron, right? It's got that 1 valence electron. It wants to give that up because underneath it's got that nice filled outer shell that it'd like to have. If I look at chlorine, okay, chlorine has an inner filled shell. Both of these also have an inner shell with 2 electrons to start out. Okay. But chlorine has 7 outer electrons. So chlorine really wants to attract an electron. Sodium wants to give up 1 because if it gives it up, then it has a filled outer shell. Chlorine really wants 1 because if it attracts 1, then it has a filled outer shell. So what's going to happen here is that sodium is going to be like, hey, take my electron. Chlorine's going to be like, hey, thanks for the electron. Well, when sodium gives up an electron, what happens to it? Remember, those electrons are negatively charged. So if sodium gives up a negatively charged particle, sodium becomes positive. Right? And then what happens to chlorine when it gains a negatively charged particle? It becomes negative. So this will become positive 1, that will become negative 1. Well, remember, opposites attract, right? When we have opposite charges, they're going to come really close to one another, and they're going to form a bond and become NaCl. Okay, NaCl. And what you actually see with your salt, okay, when they bond together, so this is my sodium, this is my chlorine, right? They're both different sizes based on atomic radius. What happens is they get around a bunch of other sodium chlorides and they build this nice little crystal lattice structure. Okay, remember this is positive, this is negative. Well, what happens is that you get another chlorine and sodium close to one another. They'll bond together as well. And then you start getting this nice little crystal structure that is our salt that we have at our tables. Okay, obviously it's got some more things in there like iodine, which is a nice nutrient that we need, okay, that we get from iodized salt, right? So if you're using Himalayan salt or sea salt, okay, you're not getting that iodine that you need. So make sure you're using good old-fashioned iodized table salt every now and then so you get that iodine. It's good for your thyroid, stuff like that. Either way, I'm not a dietitian, okay? So this is ionic bonding. We're transferring an electron, right? And this happens with something on the left side of that stair step, a metal, something on the right side of that stair step, a non-metal. So this is what we got to do. We got to start looking at our charges. Okay, we got to start looking at the charges on the periodic table. Let's do a brief overview of those real quick. So, again, here's the outline of the periodic table. Okay? Remember, if it's in hydrogen's column, they all have a +1 charge. Hydrogen has a +1 charge. They like to have a +1 charge. They like to give up an electron. That's why it's +1. Everything in beryllium's row has +2. We skip the transition metals for now. We'll deal with that at another day. Boron's row, or column, sorry, has +3. Carbons has plus or minus 4. Nitrogens has minus 3. Oxygens has minus 2. Fluorine minus 1. And helium's column is 0. Okay, you need to know those charges. Go ahead and put them on your periodic table. Okay, these are what they like to ionize into. Okay, beryllium likes to give up 2 electrons. Boron likes to give up 3 electrons. Fluorine likes to gain an electron. That's why it's -1. Oxygen likes to gain 2 electrons. That's why it's -2. So make sure you're aware of those charges. Okay, you got them written down in your periodic table somewhere, because we are going to start talking about combining these ions. Okay. One thing with ionic bonding that you need to know is that the positive ion, or the cation, always goes first. So you'll see a bunch of examples coming up, like MgCl, MgF2, let's go with K2O, or AlN. Okay, in these examples, which you're going to be making these formulas here in a little bit, the cation is always first, or the metal is always first. So if you notice, like, these are all the charges on these individual ions. Okay, and as you'll see, the positive ion is always listed first in these compounds. Make sure that you're doing that. You're never going to see something like ClNa or OK2. Alright, you're always going to have the positive ion in front. Okay, so be aware of that. You're always going to have the metal, the cation in front, the anion, the nonmetal as second or on the back end. Okay, so say no to that, say yes to that format. Na plus and Cl minus. We're going to start combining these ions, right? When we combine them, you have to make sure that your overall charge is 0. Okay? We don't want a compound that has a minus charge or a positive charge. We'll deal with that another day. From here on out, all our compounds are going to be neutral. They like to be neutral. They like to balance each other out. So when I combine these two ions, they are going to form NaCl. NaCl. And then we got to be able to name this guy. Okay, so what we do is we just say the first element, which is sodium. And then for the second element, we keep the prefix of it. So chlorine's prefix, or first syllable, is chlor. So we keep the first prefix, and then we add "ide" to the end of it, right? You know this as sodium chloride. So for the first element, we just say its name. For the second element, we keep the prefix, so it was chlorine. We kept chlor, and we just changed it to "ide." Okay, so sodium chloride. Oxygen would become oxide. Fluorine would become fluoride. Bromine would become bromide. Okay, and so on and so forth. And that's just for the second element. Okay, so that's a real easy one. It was a +1, -1 charge. They're just bonding together to make sodium chloride. Let's do another one. We got magnesium, and we want to bond it to chlorine. Okay. First thing I got to do, I got to go ahead and I got to look at the charges on these guys. Okay, I look for magnesium on the periodic table. It's in that second column, okay, in that alkaline earth metals. All those guys have a +2 charge. Chlorine. Chlorine, it's a halogen. It's all the way on the right. It's in that -1 column, so it's got a -1 charge. Okay, here's where things get tricky. You gotta make sure that these charges balance out. They can't have a negative charge when they're combined or a positive charge when they're combined. They have to be neutral. So if I combine these right now, magnesium would have a +2 charge, chlorine would have a -1 charge. Overall, it'd have a +1 charge. So what do we need in order to make this thing neutral? What we do is we add another chlorine. Okay. Now we have a +2 charge from this one magnesium. We got a -2 charge from both of these chlorines. Okay, so +2 -2 equals 0. All right. Well, when we combine these guys, okay, we'll write it as MgCl2, where that 2 tells us that we have 2 chlorines. Okay, 2 chlorines. So we don't put a 1 here, okay? There is an imaginary 1 there. We just don't put a 1 there because it's just inferred that there's 1, okay? But for this one, it's just MgCl2. Let me get rid of that mark. Right, here it was a 1-to-1 ratio, so it was just NaCl. Here it's a 1-to-2 ratio, so it's MgCl2. Always remember these tiny numbers tells you how many atoms there are in that compound. All right, what's the name of this guy? We combine them, right? First element we just say is magnesium. And then Cl, chlorine, just becomes chloride. It doesn't matter if there's 2, 3, 4, or 6 of them, it's just chloride, okay? Now, in the future, when we do covalent bonding, you'll start to run into things like oxygen difluoride or tetrasulfur monoxide, okay? We'll deal with that when we get to it. Right now we're dealing with ionic bonds, so it's just this process. First element, second element, you keep the prefix and add "ide" to the end. Let's do another one, a little trickier one, okay? How about magnesium and oxygen? Magnesium and oxygen. We gotta look at the charges first, right? When we want to combine these ions, we gotta make sure they are neutral. Magnesium has a +2 charge. Okay. Oxygen has a -2 charge. It's in those group over to the right. It's a non-metal, but it's in that column that are all -2. Do I need to have, if I combine these right now, is the charge going to be neutral? And the answer is yes. It's just fine. +2, -2, they combine, they're going to be neutral. So I can just leave it as MgO, right? MgO is just magnesium, right? We say the first element. Oxygen, right? We keep the first prefix, with which is oxygen, is ox, and add "ide" to the end. Magnesium oxide, okay? These are both salts, okay? Salt that they put in food. Magnesium chloride is also a salt, okay? And they put it in like Powerade and things like that. They say they got different electrolytes, okay? Those electrolytes are just different types of salt, all right? They also put like potassium chloride and some other types of salt in there. Okay, maybe it's magnesium sulfate. Sometimes it's delivered in another way, but it's just magnesium they're giving you. Last one that will make challenging, okay? I'm going to move this first one. We're going to do aluminum and oxygen. Aluminum and oxygen. Okay, aluminum oxide, which is just when aluminum kind of oxidizes, and it's the rust form of aluminum. If you guys don't get much oxidation around here because you don't have salts on the road, but in Indiana they got those new Fords that have aluminum bodies. When they oxidize, it gets kind of like a white oxidation on it. It looks like it eats away the metal a little bit, but it's not like that brown rust you see. It's just this nice kind of white glaze over the metal. So anyway, let's just look at this charges. Aluminum. If I look at it, it's right underneath boron. Those are those +3 charged atom. Oxygen, as we saw before, has a 2- charge, or a -2 charge. Okay, here, again, we got to balance it. This is a little tricky. Okay, we can't have like half of an atom. Okay, we got to deal with whole numbers. So really what we got to deal with here, or got to find here, is what is the lowest common number that 3 and 2 can become so that we can neutralize them, okay? So we have +3 and -2, 3 and 2. What's the lowest number that both those numbers can go into? And that answer is 6, right? If I get a +6 charge and a -6 charge, they'll neutralize each other out, and then we're good to go, okay? So again, to neutralize it, if we combine them now, it'd give us +1, but we need to neutralize it to give it a 0 charge. And to do that, we got to get them both to plus and minus 6. So if we move this over and we combine them, aluminum has a plus 3 charge. To get that to plus 6, how many aluminums would we need? We need 2, right? Now all the aluminum have a plus 6 charge. To get oxygen to minus 6, how many would we need? 3. We would need 3 oxygens. Remember, these numbers tell us how many of each atom we have. So all those aluminums have a plus 6 charge. All those oxygens have a minus 6 charge. And now we name it. And it'll become aluminum as our first element. And again, oxygen, oxide. Okay. I know I said last one. I'll leave one more up here for you to do. And that'll be that. Okay, I'm just going to pick one off of the board. Let's do KS. KS. All right. I look for K. It's in that very first column. It's got a plus 1 charge. Sulfur is on the right side. It's right underneath oxygen. It's going to have a 2 minus charge. Again, remember, we got to have this neutral. So sulfur has a 2 minus charge. Potassium has a plus 1 charge. I'm just going to need another potassium. That way, I have 2 plus on the left side and 2 minus on the right side. So I'm going to need 2 potassiums, just 1 sulfur. K is potassium. S is sulfur. We keep that first prefix of sulf. And add ide to the end, potassium sulfide. Okay? That is the main thing of ionic bonding. Make sure you're balancing your charges, looking at your charges, making them the same, and have yourselves a good day.